This is Mrs. Palmer-Quay with the third video for Module 10. In this video, I'm going to talk to you about titration, which will bring in some of the things we've already talked about with molarity and the dilution equation. Now remember when I was beginning to talk about acids and bases in that first video for this module, I told you that an acid can be neutralized by a base, and a base can be neutralized by an acid. This especially pertains to areneous acids and bases. Remember those ones where they are going to form a salt and water when they react together? Areneous acids give up a hydrogen and areneous bases give up a hydroxide. So a hydrogen ion plus a hydroxide ion makes H2O. Remember also that the pH of water is 7, right in the middle of the pH scale that runs from 1 to 14. And so something that has been perfectly neutralized would have a pH of 7. Titration uses this neutralization reaction to determine the concentration of an unknown acid or base. There are some other ways that we use titration that I'll talk about at the very end of this video. But we're going to be focusing right now on acid and base neutralization. So if you have a neutralizing solution that you know the concentration, and you have an indicator, then you can determine the concentration of your unknown. An indicator is something that will tell you when neutralization has occurred. Most often this is a chemical that will change color as pH changes. It changes its color at what's known as the end point, and that is representing the equivalence point, where the number of hydrogen ions is equal to the number of hydroxide ions. When you have 3 out of the 4 things in the dilution equation for a titration, then you can use it to determine the concentration of the unknown. So if you know the molarity of the acid you are working with, and how much you needed to neutralize the base, then you can figure out the base given you know its volume that you started with. So the dilution equation is just rewritten using A for acid and B for base instead of 1 and 2 to represent the solutions. This is the standard setup for a titration experiment. You have your flask that contains your unknown solution. And then you have a burette, that's what this glass piece of equipment is, that contains a known concentration of your neutralizing solution. The examples here is that we have an acid in the flask and sodium hydroxide or a base in the burette. You add your indicator so that this is one that's going to turn. You can see it's starting to turn a little bit purple here. So the indicator is put into the acid, and then you slowly add your neutralizing solution, the sodium hydroxide, until you start to see a color change, and we'll be swirling this the whole time so that you know that it is well mixed. When the color has changed and stays changed permanently, then you know you have reached the end point, which is representing the equivalence point where the amount of hydroxide and hydrogen ions have now combined to make water in equal amounts, and you have a pH close to 7. Phenolphthalein is the indicator that we will be using in our lab experiment. We don't have burettes, so we'll be doing a micro-scale titration with eyedroppers and the well plates. But the process is still the same. You want to add your sodium hydroxide until you reach this equivalence point. A point where there is a little bit of pink color, but not too much. And so you can see here that you're starting to get a slight bit of pink. You can kind of see it on the test tubes right here at the interface between the test tube and the phenolphthalein solution and the air, about somewhere around the pH of 8. And then any point after that, you're going to be darker and darker pink. So you're looking for just the first shading of pink that does not go away. This graph down here on the bottom is showing the pH of your acid or whatever you're testing here, but in this case we'd be testing an acid because phenolphthalein changes as pH rises. So we're going to be taking our original solution that's starting at a low pH, acidic pH, and adding base to it so that it's going to be increasing. And so then across the bottom of this graph would be the amount of our neutralizing solution. As you can see from this graph, your pH will slowly rise as we add more of our sodium hydroxide. And then when we get to the equivalence point, it has a very rapid rise accompanied by a color change of the phenolphthalein indicator. And then if we were to continue to add more of the base, there would be again sort of a slow rise in pH. Titration problems using the dilution equation, or using that dilution equation as your base, will look something like this. This problem asks you, it says if you have 20.7 milliliters of a 0.5 molar sodium hydroxide solution, and that's how much is required to neutralize 15 milliliters of hydrochloric acid, well then what is the molarity of the acid? So we know that the molarity of the acid times the volume used of the acid is going to equal the molarity of the base times the volume of the base. And so we just plug in numbers. We're trying to figure out the molarity of the acid, so that would be our X. The volume of the acid is 15 milliliters. The molarity of your base is 0.5. And the volume of your base is 20.7 milliliters. And you would just solve this algebraically, and you'll find out that the molarity of our acid is going to be 0.690 molar for this hydrochloric acid. So it's really pretty straightforward. If you've got the dilution equation, if you've worked with that enough so you're comfortable with that, you're plugging in and solving things basically the same way. Now notice here we have sodium hydroxide plus hydrochloric acid. It will give us sodium chloride and water. And the ratio between our sodium hydroxide and our hydrochloric acid is 1:1. Because this is a monoprotic acid, it only gives up one hydrogen ion and one hydroxide ion. So it's a 1:1 ratio. If you have a polyprotic acid or base, you do need to take a slightly different approach to these kinds of problems. So just to review, the polyprotic acids contribute more than one hydrogen ion. So we've got phosphoric acid here, H3PO4, and it can give off 3 hydrogen ions if the reaction is able to proceed to the full endpoint. At the endpoint of a titration reaction, the equivalency point, you've got the moles of hydrogen ions equaling to the moles of hydroxide ion. But if there are 3 times as many moles of hydrogen being able to be contributed by the acid, like you have in this example of phosphoric acid, then obviously you'd need 3 times as much hydroxide ion to even them out. So you need to be careful about considering the ratio of the acid or the ion contributed by the acid to the hydroxide contributed by the base if you have a polyprotic acid. This question asks, what is the molarity of a solution of sulfuric acid if 32.2 milliliters of a 0.25 molar sodium hydroxide solution is required to neutralize 26.6 milliliters of acid? We need to start with a balanced equation so we can see what's going on. So sulfuric acid is H2SO4. And we're going to react that with sodium hydroxide. And these reactions, remember, are going to make a salt and water. And so our salt is going to be sodium sulfate. And since we know that the sulfate ion has a charge of -2, we need 2 sodiums there in the formula, and then water. So of course we need to balance the equation by putting a 2 in front of our sodium hydroxide. And so that will give us our 2 in front of water as well to balance this equation. What we're most concerned about is the relationship then between the acid and the base, that we're going to need twice as much base as acid, 2 moles of sodium hydroxide is needed to react with 1 mole of sulfuric acid, because sulfuric acid is a polyprotic acid. So after you make the balanced equation and take a look at your mole ratio, then you want to figure out how many moles of sodium hydroxide were in the solution, the amount of solution we used. And remember that molarity is equal to moles per liter. So in this case, we're trying to figure out the moles, and so moles are going to be equal to the molarity times the liters. The molarity then of our sodium hydroxide given in the equation is 0.250, and then the liters were 32.2. Oh, sorry, that's milliliters. We have to turn it into liters. I need to remember this myself. So this would be 0.032 liters. And so molarity then is moles over liters. Things are going to cancel out. And so that the number of moles of sodium hydroxide, because this is what we're calculating first, we do have the molarity and the volume for sodium hydroxide, but the amount is 8.05 times 10 to the negative 3 moles, putting that into nice scientific notation. So now we have our moles of sodium hydroxide. Remember, it's 2-to-1 ratio, so we're going to only need half as much sulfuric acid because it is able to provide 2 hydrogens for every mole of reactant, or 2 moles of hydrogens, and so we're only going to need 4.03 times 10 to the negative 3 moles of the sulfuric acid. So then the question is, what's going to be our molarity? We have the moles of the sulfuric acid. We know how much the milliliters are. So in this case, we're not using the dilution equation at all. We're still sticking with our molarity. We've got moles and we've got liters, so we take our moles and divide that by liters. So that would be 0.0266 liters. And so then that gives us a molarity of 0.151 molar. So as you can see, there is a difference in how you attack these problems depending upon whether you have a monoprotic or a polyprotic acid. And just to end, I wanted to give you a couple of examples of titration in real life. These are not necessarily acid-base titration reactions, but there are reactions where you're testing the concentration of a reactant in a chemical reaction by incorporating it into some substance that has another reactant, and you're measuring the product, or you're measuring a color change, or you're measuring perhaps electrical conductivity, depending upon what exactly is being titrated. So the home glucose monitors that people who are diabetic use, the indicator there, it's a titration equation that will be able to give a glucose value. If you have an aquarium or a pool, you're using titration all the time with color change to determine the concentration of various things in that water. And many of our medical tests really are titrations because it's such a good method for determining the concentration of a substance. So this finishes up what I want to say in this third video for Module 10.